Hello everyone, I'm Kosei Sakamoto from University of Hyogo. In this video, I talk about our paper, Warp Revisiting Generalized Facial Network for Lightweight 128-bit block cipher. So this is a joint work with Subhadeep, Banik, Zhenzhen, Takanori, Isobe, Hiroyasu, Kubo, Fukang, Kazuhiko, Minematsu, Shibata, and Maki, Shigeri. So this is the outline of this presentation. Since proposed the first lightweight block cipher present, many numbers of lightweight block ciphers have been proposed. As the first generation lightweight block ciphers, some primitives for the small area were proposed. For example, present, Catan, print cipher, LED, and so on. So these block ciphers have less than 128-bit blocks for achieving a very small hardware footprint. So these ciphers very contributed to the development of field of lightweight block ciphers. So however, in the real world, there are some problems with these ciphers. So when we consider the use case in the block cipher mode, most of the popular modes have birthday 1 security. So it means 2 to the power n second input blocks are sufficient to break with n-bit block ciphers. So 64-bit block ciphers are not suitable with this mode. So if block cipher has a 128-bit blocks and 120-bit key, the block cipher mode is guaranteed to require 2 to the power 64 blocks to be broken. And it is not practical. Moreover, it is also possible to directly replace with AES 128. For these reasons, our goal is to build a 128-bit block ciphers based on generalized facial network with significantly small both encryption only and unified LED circuits than existing ciphers. So a small unified LED circuit is useful for some popular mode, for example CBC, OCB, and XTS mode. So for achieving a small unified LED circuit, we employ generalized facial-based ciphers which can achieve a smaller unified LED circuit than SPN cipher. So in our paper, we propose a new 128-bit block cipher named Warp. So Warp is based on Type 2 generalized facial network with 32 branch with a 128-bit key, and Warp requires only 763 gates for a bit serious encryption only circuit. It's a new circuit record of a 128-bit block cipher. So in this section, I explain the specification of Warp. So as mentioned before, Warp is a 128-bit block cipher with a 128-bit key. The round number is 41. So the round function is based on Type 2 generalized facial network with 32 branch permutation and 4-bit S-box. And Warp has a very simply key scheduling function. Here, I elaborate on the components of Warp. First, I explain the round function. So this figure is the round function of Warp. So as for the S-box, Warp used 4-bit S-box, SP0 used in Midori. So S-box is applied to each even number branch. So as for the round key, 16 4-bit round keys are XORed to internal value after S-box. The round constant of Warp is LFSR based round constant. So round constant RC0 and RC1 are XORed to the first branch and the third branch before applying permutation respectively. So as for permutation, Warp has a 32 branch permutation, which is suitable for fast diffusion and resistance against major attacks. And permutation is omitted at the last round. So next, I explain the key scheduling function of warp. So warp has a very simple key scheduling function. The original key is divided into two 64-bit halves. Then, they are alternately inserted into the round function for every round. So, in this section, I explain the design rationales of warp. So first, we consider permutation and S-box in order to explain why warp employ not 60 branch but 32 branch. So as for permutation, it is much more difficult to find a good 32 branch permutation than the case of 60 branch permutation in terms of security. So because the number of candidates of 32 branch permutation is too much. So as for S-box, an 8-bit S-box is much inferior to 4-bit S-box in terms of size, delay, and energy. So in short, if we find a good 32 branch permutation, we can construct a better block cipher than one with 60 branch in terms of size, delay, and energy. So for permutation in generalized spatial network, Suzaki and Minematsu showed the diffusion round about permutation with up to 60 branches at FSE 2010. So the diffusion round is very important. So because it directly related to the resistance of some attacks. So as a construction with generalized spatial network with 60 branch permutations, 64-bit block cipher, twine, and L block were proposed. So both of which achieve a best diffusion round which matches with this Minematsu and Suzaki's paper. So as for construction of 32 branch, there are some primitives that have rotation as a linear layer, not permutation. However, so there is no design achieving a better diffusion based on permutation. So this is because finding a good permutation much more difficult due to the number of candidates is about 2 to the power 88. So therefore, our challenge is to find a good 32 branch permutation for diffusion and the number of active S-boxes. So as said in the previous slide, so the number of candidates of the 32 branch permutation is too large. So to solve this problem, we convert the GFN type structure into the L block-like structures, which consist of 60 branch permutation and 60 branch rotation. So by this conversion, we can reduce the candidates to about 2 to the power 48. So, however, it is still too large to search all of them. So for more reducing candidates, we limit 60 branch permutation to two same 8 branch permutations. That is helpful for better hardware implementations. So by these limitations, a total number of candidates are reduced to about 2 to the power 19. So it is possible to search all of them. So next, we find a good 32 branch permutation. So we mean that a good permutation is to satisfy the following two features. The first feature is achieving fast diffusion, which means 10-round full diffusion in our design. So another feature is to have fast growth for the number of active S-boxes. So generally, calculation for the lower bound of the number of active S-boxes is much heavier than 1 for diffusion round. So therefore, we take the following 3-step search approach to find a good permutation. So in the first step, we evaluate the diffusion round for all 2 to the power 19 candidates. So as a result of the first step, so we obtain 152 candidates, each of which achieve 10 round full diffusion. So in the second step, we evaluate the lower bound of the number of differentially active S-boxes for 152 candidates by MILP. So as a result of second step, there was no candidates more than 64 activated S-boxes over 80 round. And 21 candidates achieved more than 64 active S-boxes over 19 round. So moreover, 8 candidates of 21 achieved 66 active S-boxes over 19 round. Lastly, in the third step, we evaluate resistance against integral attacks and impossible differential attacks. So as a result of the third step, we find that 8 candidates are identical for linear active S-boxes and the longest round of impossible differential and integral characteristics. Although these 8 candidates have identical for our search, they are not isomorphic as far as our study. So since it is no difference from the implementation aspect, so we arbitrarily choose one among 8 candidates. So this is a block-like structure of warp. So 8 branch permutation warp is shown in this table, and 60 branch rotation warp is a 6-word right shift rotation. And our hardware implementations are based on this ray block-like structure. So this slide shows how to convert to the ray block-like structure. So as you can see, we need to add permutation to input and output for conversion. So for more detail of this conversion, please see our paper. So in this slide, I explain our requirements for 4-bit S-box. For security, we require the maximal probability of differential is 2 to the power minus 2, and maximal absolute bias of linear approximation is 2 to the power minus 2. So for implementation, we want S-box to belong to one of the 30 cubic classes for which the S-box is decomposable as the composition of 2 quadratic S-boxes. So for these requirements, a 4-bit S-box SP0 used in Midori is suitable for our design. So therefore, we used SP0 as S-box in warp. So at the end of design rationales, I explain the key schedule and round constant. So as for the key schedule, we require only multiplexer to filter appropriate portion of the round key in each round. So it is beneficial to unify the circuit. Therefore, we apply alternately the upper and lower half of the 128-bit key to alternate rounds. As for the round constant, we use LFSR-based round constant, so it is efficient for hardware implementation. So here, I show result of our security evaluation. So we evaluated resistance of differential attack, linear attack, impossible differential attack, integral attack, meet in the middle attack, and invariant subspace attack. So as for differential attack and linear attack, so we calculate the lower bound of the number of differentially and linearly active S-boxes by MILP. So our evaluation is based on nibble-wise truncated differential and linear characteristics. And we use Groby Optimizer as the MILP solver. So as shown in design rationals, as the number of differentially active boxes reach more than 64 active boxes over 19 rounds. So for linearly active boxes, the number of linearly active boxes is identical to the one of differentially active boxes for each round. So as for the impossible differential attack, we searched the longest impossible differential characteristics by MILP. So in our search, we gave one active bit to both over encryption and decryption side. So as a result, we find 21 round impossible differential characteristics. And based on it, a key recovery attack is expected to work up to a 32 round warp. So this attack is the most efficient attack for warp among our security evaluation. So then, I simply explain other attacks result. So first, as for the integral attacks, so we find a 20 round integral distinguisher based on nibble-wise division property by MILP. So as for the meter in the middle attacks, we expect that it is difficult to mount a 32 round attack on warp. So as for the invariant subspace attack, we expect that it doesn't work for full round warp. So in this section, I explain hardware and software implementation results. So in this slide, so I show the hardware implementation results about serial implementation results synthesized with STM 90nm standard cell library. In this table, we compared with other 128-bit block ciphers. So as you can see in this table, warp perform well in terms of area. So encryption-only bit serial version is only 763 gates, and it is the best record of the 128-bit block cipher. So this table shows the round-based implementation result, synthesized with STM 90nm standard cell library. So similar to serial implementations, warp requires smaller areas than other ciphers. So also, warp achieves a notably low energy consumption. So summarizing the hardware implementation results, warp achieves the smallest hardware areas for both the round-based and serial circuit. And energy consumption of multi-round circuit is quite small. It is comparable to Midori 128. So next, as for the software implementation result, warp also perform very well. So as shown in this table, warp achieve competitively small core size and extremely low RAM consumption on 8-bit microcontrollers. So finally, I talk the conclusion of my presentation. So in our paper, we propose the new 128-bit block cipher warp. So warp is based on variant of type 2 generalized space network with 32 branch combined with the improve the over 32 nibbles to boost the diffusion. So the main goal of warp is to achieve a small footprint both for encryption only and unified AD circuit. So as for performance, so hardware implementation of warp is the smallest compared with other 128-bit block ciphers. And software implementation is also very competitive with other 128-bit block ciphers. So these are references of my presentation. So this is the end of my presentation. Thank you for your attention.